I want to start first with a quick little engineering moment. It's going to help you on this lab and especially future labs. There's three dimensionless numbers you should always be thinking about when you're doing an experiment. And one's pretty obvious, the other two may not be so obvious. So someone tell me, what's probably the big obvious dimensionless number that you always need to be kind of aware of? Reynolds number, yeah. And what's the critical number there, and what's it describing? Anyone remember?
Wait, by critical number, do you mean like the cutting
value? What's the value? Anyone remember?
Is it 2,500?
23. So 2,300, and that tells you the difference between, between what, turbulent and laminar. So that one's going to be very useful, especially on some other labs. This lab, you really don't care if it's laminar or turbulent in the sense that all you're really looking at is pressure drops. What's the second dimensionless number? You're probably not going to think of this one. It's not Nusselt number. It's not Prandtl number. You have to worry about those if you're dealing with heat transfer, but it has to do with compressed gases. And if you have to worry about compressible effects, does anyone know what number that is? You probably didn't talk too much about it in fluids, but it's the Mach number. Mach number is the ratio of the speed to the speed of sound in that material. And there's actually two critical numbers you want to worry about there. Mach 1 means that we're going to be choked. You probably remember that from maybe your 285 class, the lab you did. And then the other one is Mach 0.3. Does anyone know what that tells me? It tells me if I have to deal with compressible effects or if I can consider my fluid as incompressible. And that usually happens with a gas. It's very hard to get a Mach number of 0.3 if you're flowing a liquid. If you're flowing a gas, it's actually pretty easy to get above Mach 0.3. And you always assume it's compressible. Almost. And so kind of want to be aware of that. And then the last number, which is pretty applicable to your lab, and I think we may have talked about this with a couple of the groups, is the compressibility, which sounds like it's the same thing as the Mach number, but I'm talking about the thermodynamic compressibility, Z. And what does Z tell me?
How far it deviates from ideality? Yeah.
Yeah, ideal gas. Can I use ideal gas? And that's something you're going to care about in this lab. And so I think I told some of you in your thermo book, there's a section that says, when can I use ideal gas? In my version 7 book, it's on page about 104, but you get a graph that looks like this. And the section heading says, conditions of approximate validity of the ideal gas equation. And in fact, I started my Instagram account a few years ago just because students kept asking me, can I use ideal gas? And I said, I never want you to ask me that again because you can figure that out. It's right there in your textbook. That figure has TR and PR, and then it gives you the region where you're within 2% of ideality for that given TR and PR, which is in general high temperature, low pressure. And so you're going to probably want to check that out. Can I use ideal gas? Or calculate the compressibility factor for your conditions so that you can determine if you've got ideal gas conditions or not. So those are some pretty practical things to remember, and you're going to want to remember those especially as you go along this lab and future labs. Okay, stats. That is our big goal today. And we're going to motivate this by, I think you see the pipe viscometer, the control panel on your screen. I'm going to turn it on and we're just going to generate some real-time data. And right now I have it in manual mode. This pipe viscometer 2 changes the flow rate because it has a variable speed pump. That's not super common. The other side of this, pipe viscometer 1, does not have a variable speed pump. And so you have a valve that opens and closes. When Mike's, this used to only be one system. When Mike split the system, he didn't want to buy another valve. We kind of talked about how expensive they are. And so he got a variable speed pump. And so I'm going to turn this on. I got it at about 89%, whatever, of percent speed. I turn it on, and what we're going to measure right here, you see the flow. Oh, there we go. You're going to see the flow rate start to go up, and you're going to see the pressure drop start to change. And this is going to give me something close to about 7.2. Nothing special about that. That's just kind of what I used yesterday when I was doing this lecture. And I'm going to actually put it in auto mode when it's close to that so that it will get down to about 7.2. And what we're going to do is we're going to kind of read off the pressure drop. And now someone tell me what this quotes WC is that's also applicable to your lab.
Inches of water column.
Inches water column. And why such a weird unit?
Scaling, right? Because you don't, otherwise you'd have a really small number that would be hard to use, right?
That's right. So if I had PSI here, you'd have a small little fractional number. Lots of zeros, 0, 0, 0, 0.000 something. And so we do this so that you get some reasonable numbers here. And so what we want to record here is something like, what is the at 7.2 gallons per minute? We're going to record the delta P. And so what is it, about 43.4, let's call it. Now here's the very first thing I want you to remember. I need to generate more data. I want more data points. Why can't I just wait around here? Or why can't I just say, okay, I'm going to say 10 seconds per points, 3 seconds. Let me record some data here. Why couldn't I just take 100 data points here and say, okay, now I have 100 points I can do my stats on, and I'm going to have fantastic error bars. Or another way to say that, let me bring up this Excel sheet once it's done, so I can emphasize what I'm asking here. Sorry, give me 1 second. I get to go over here. Yes. So here's my flow rates. Why can't I say I have 3 points now of flow rates and 3 pressures and do some stats on that? That is incorrect.
Flow hasn't really developed?
No, not necessarily. If you kind of look back, my flow has, you know, it's pretty well steady state, right? 7.2, 43.4. It's not that it hasn't developed. It's because these are not independent samples. They are all correlated. Statistics only works if you have independent samples. And these are literally correlated in time. What I have to do is come over here, and there's a couple things I can do. I'm going to put this back in manual mode, and then I'm going to turn the pump off. I'm going to go away from my set point, turn the system off or do something, and then I'm going to turn it back on. But I can't just get it to steady state and take a bunch of data and consider those independent points, because they're not. But here I've gone away, I've allowed the system to do something to change, and now I'm going to turn the pump back on. We're going to see what pressure drop we get. And this would be a fairly good independent sample. I've gone away and then I've come back. Now, that's a little dependent on how quickly your system gets to steady state. If I was trying to calculate what is the average temperature on September 11th, I can't just say, okay, I'm going to take temperatures today and I'm going to take 5 temperatures today, because I've got historical data that is going to change that. And so you have to kind of think of the timescales here. These timescales are fairly quick. They come to steady state fairly quick. And so by just turning off and turning on, I can get an independent sample. I'm a little high here, so I turn my controller on. It should start going down, and then we'll record what the pressure drop is.
Dr. Knott?
Yeah.
This is kind of, it may be irrelevant, but when you open the Excel file, why did the time show up in like 8,500 seconds instead of starting at
we
0?
kind of talked about that, but let me explain this again. These are just, this is the second time since the controller was last started. And so all that really matters is the difference between the numbers. And so if I was doing this, I'd do something like this and then copy it down. And so that's really what the difference in numbers are there. So the first point was taken after 0.62 seconds and then after 10 seconds. And I think on all the data you were given, we kind of already did that, but that's what it is.
Thanks.
Okay, now we're at 7.2 again. We're at 43.4. Oh, we're looking like we got some pretty good, it's bouncing around a little, we'll see. But another thing I could do is, okay, I could say, let's go down to 3 gallons per minute or 4 gallons per minute, take a data point, let it get to steady state there, and then go back to 7.2 gallons per minute. And then that's another way I could get independence. But what I can't do is let it get to steady state and then take a ton of data, because those are not independent points. And all the stats you learned with normal distributions are independent. So any question on that? That's the first thing you always want to remember when you're doing an example or doing a experiment, is these are not independent points. I cannot record this as 3 points. So if I was going to actually use these data, there's 2 things I could do. I could either say, okay, for this experimental run, I could say my flow, I could either pick one of these points and use it because any of them are just as valid, or I could just average these and say this is 1 point. So I'm going to say for this run, my average or my flow rate was 7.21 gallons per minute. And then my pressure drop was 43.44. Does that make sense? And then I could open up another Excel sheet after I let this thing get to steady state. I'm going to go back up now to 7.2. And this, if I was doing this, would kind of be my third independent sample here. But the point I want you to remember is these are not independent in this Excel sheet. You didn't change anything. It's all at steady state. So that's really only one independent point to count as your statistics. And probably if I was doing it, I would use these 2 points here, the 7.2 for my flow rate, the 43.44 for my pressure drop. So let's say I do this same experiment. I turn it off and turn it on, or I go away and come back to 7.2. And I get a 43.5 and a 43.2 and a 43.4 again. What am I going to, so all these, theoretically, I would have had, what, 5 different Excel files like this. And I would have gotten 5 different averages. And then this number may have been the first one. And this next Excel file would have been the second one. So I've got 5 independent points. That's the first thing you want to do. Nate, go ahead.
So I was just wondering, we're taking the average there. Do we not need to like check for outliers or anything with that since they're not independent points?
So if I was taking this data and it was, and it wasn't at steady state yet, then I probably would throw out the whole set. And so what I usually want to do is I want to see if it changes over time, because I'm trying to get some equilibrium steady state value out of this. Does that make sense?
Gotcha. Yeah, no, that makes sense.
So if I would already have checked that and say I already waited an hour for this thing to get to steady state, or this one comes to steady state fairly quickly, you can see that just in the time we're talking, right? Now we're at about 43.2-ish. And so we got a point here. Why don't I always get back to the exact same value? Any ideas on that? Why do, even though I am trying to get back to 7.2 gallons per minute, why isn't the pressure, even with this controlled system, why isn't it always the same? Any ideas?
So would the flow in the system be consistently turbulent or laminar? Like for whatever it is, would it be consistent enough that you'd have an identical delta P? Because the deviations are pretty small in terms of the overall pressure drop. And so it could just be little minor fluctuations.
Yeah, this is
depending on how
just the
turbulent
fact
it is
that,
each point.
right? You're pulling from a sample. There's random things. I could have errors in my measurement devices, right, that are randomly fluctuating when I take data. I've got my controller that's doing things. I've got maybe there's some sort of weird thing in my pressure lines, but you're trying to figure out all these random things that can happen. And that's why you're doing the stats, is because if you only look at one specific experiment, a variety of things could have happened. So you want to repeat it to make sure that you get what we think is the correct value. Okay, so what would you report then? What's the first thing you would do now? I've got 5 independent samples. What are you going to report as the delta P at 7.2 gallons per minute based on your 5 experiments? This is not a trick question.
You just report the average?
Yeah, so I'm going to report an average. But the bigger question is, what am I going to report as the error? While you're thinking about that, I want an answer there. I'm just going to put a couple things in my Excel file right here that we're going to talk about. What would you report for your error? It's okay. You don't have to have the right answer here. I just want to see kind of where your thinking is.
Standard deviation.
Okay, let's calculate a standard deviation. Just to emphasize what's going on here, I'll put a little double line. So let's calculate a standard deviation, because this is an important concept here. You want to watch the functions we're going to use. As I do STDEV, you can see there's multiple functions I can bring up. You might have to zoom in a little bit. I'll try to zoom in and see if that makes it bigger. Notice I've got a .p, a .s. I've got some others here that we don't necessarily need to worry about, but I've also got one that has these little caution symbols that say STDEV and STDEVP. What's the difference, first of all, between .p and .s? And which one do you want?
I'm pretty sure it's sample versus population.
It is sample versus population. So which one do you want if you're calculating the standard deviation right now?
Because you have a small sample, I believe you want .s.
Yeah, we do want S. So let me do that one. And you almost always want S, especially whenever you're doing experiments in science or engineering, because we never have all the sample. It would take infinite time. I'd have to sit here forever and ever taking data on the system to get the entire sample. The only time you really have the whole population, the only time you really have the whole population is if somehow, if all 8 of us were sitting in the UO lab right now and I said, what's the standard deviation of the heights of the 8 people in this room? Then I have made the sample very defined and I could use stdev.p. So what we really have is you may have, I'm going to put 2 things here. I'm going to put an S here and then I'm going to put a sigma. What we just calculated was S. What's the relationship between S and sigma? Do you remember from stats? Any idea what I mean by that? S is our estimate of what the true standard deviation is of the population. So this is our estimate, this is the true. That was weird. So the estimate that we got from stdev.s is our estimate of what the true population standard deviation is. So as we take more data, what's the relationship between S and sigma? Any ideas? Let me ask this way. Let's say I did this experiment 10 more times. I sat here for about 30 minutes, went up, turned it off, turned it on. I got 10 more data points. Would you expect S, right now it's what, 0.11-ish? Would you expect S to get a lot bigger, to drive to 0 and get smaller, or stay about the same? Would you think S, if I took 10 more data points and then calculated the standard deviation, with this number right here, would it start getting bigger? Would it get smaller or drive to 0? Or would it stay about the same? This is a key question that you want straight in your mind. What's your gut tell you? Someone be brave. I know it's scary.
Smaller.
My gut tells me it depends,
Okay.
right?
That wasn't one of my answers.
So what I would say is, just thinking about it right now, if you add more data points, right? Like you were saying, if they're good data points, then wouldn't your standard deviation stay more or less the same? Like if they're in the same ballpark as your previous ones, if you were to throw a bunch of terrible numbers in there, it would lead for you to have a greater standard deviation, wouldn't it?
Yeah, definitely. So I'm assuming we're giving good data. And so you're
Okay.
saying it stays about the same.
Okay.
Hannah, what were you going to say?
I thought it might get smaller, and the reason why is because I think that it would get closer to the true value the more data points that you have.
Okay. Would it drive to 0?
No, I don't think it would ever go to 0.
Okay. So this is a key thing. Sigma never goes to 0. In what it approaches is the true standard deviation. So let me show you. I'm going to share another screen real quick on my tablet. You guys see the tablet now? So remember what a standard deviation is. If I look at my normal distribution, it's telling me how spread out the data are. When is the only time sigma would be 0? What would it look like? What would
One data point?
Yeah, it would be like a delta function, right? That's what my distribution would look like. Sigma is never 0. So what are we? So let me ask you this. Let me say this. You never want to use just standard deviation as an error then, because what do we want errors to do as we take more data? We want them to drive to 0. We want to be more sure that we know where the true mean is. So standard deviation is an important thing, and we'll talk more about this as we continue this lecture, but it's not an error. So 2 things from this little section. 1, know how to calculate standard deviation. Is it population or sample? 2, S is not an error. Don't ever just report sigma, or don't even report 2 sigma. In fact, why do people like to report 2 sigma?
Dr. Knotts, are you still sharing your screen?
Oh, sorry. I switched out. Let me go. Let me show you what I just typed. So 2 things to know. How to calculate S. S is not an error. But sometimes people say, oh, I want to do plus or minus 2 sigma. And I think that comes from an improper understanding that we kind of see here. Right, we know that plus or minus 1 sigma is like 68%. If I did 1,000 experiments, 683 of them would give me values between plus or minus 1 sigma from the average. And then plus or minus 2 sigma, if I did 1,000 experiments, then 954 of them would be within plus or minus 2 sigma. That's what sigma tells me. It's not telling me how accurate my mean is. It's just telling me the distribution, where my data would be. Okay. So we never want to use it as an error. In fact, if your standard deviation isn't just converging right to the correct value, then something's changing, and then you've got a problem with your data. Okay, so what do I want to use for my error? There's 2 answers to that. I can use what's called standard error, which is not common in engineering, or I can use a confidence interval. Standard error is related to confidence interval. Standard error is sigma divided by square root of n, which is 5 in this case. So what's causing the error to drive to 0 here? It's kind of obvious, right? I'm dividing by the square root of n. So my errors are going down as the square root of n. The more n I take, the smaller my errors. So I could report my error as, so I could say my average delta P is 43.38 plus or minus 0.05. But then I also want to specify, whenever I write an error, I want to say something like where the uncertainty is the standard error. I've got to define what I'm doing. Now, again, we don't use standard error that often in engineering, but they do that often in biology because things look a little better that way. But what we usually want to do is a confidence interval. And specifically, I'm going to do a 95% confidence interval. And we're going to talk about what that means. But the equation for confidence interval is S divided by N. It's actually the standard deviation times a t-value from the student t distribution. Now, I don't have time to teach you all student t. I'm sure you've heard of that before, but student t looks fairly similar to the normal distribution. It's just broader. It's spread out. And it's also dependent on n. As I take more n, the student t distribution becomes the normal distribution. Somewhere around n equal 30 is what people like to say a lot. Okay, and the reason student t is a little broader is because it's taking into account that we only have an estimate of sigma. S is only an estimate of what the true sample standard deviation is. And so that's why student t came up with all his math. But as far as obtaining a 95% confidence interval, you just need to know how to get a t-value. And to know that, you've got to know the difference between 2-tail and 1-tail. And you see kind of some pictures here. So I'm going to stop sharing this and I'm going to go back to my tablet because I think it's a little easier to draw on. Okay. What is a t-value? Here's what a t-value is. If I take my student t distribution, which looks like my Gaussian, looks like a normal distribution, I've got this x-axis. What a t-value is I'm trying to determine the value of the x-axis where I cover some amount of area where I am certain. So 95% in this case. 95% of the area I am certain about, and I am uncertain about 5% of the area. And the t-value is when I start integrating at negative infinity on this distribution, and I integrate until I find the x value where I get 95% of the area covered. Now, I'm not going all of the theory, why that all works. I'm just saying that's where you get t-values. And you probably didn't do the integration in stats because when they teach stats, they assume people don't know calculus, so they don't want to integrate. And so someone's already done the integration and they put it in tables or they put it in functions like in Excel. But that's where that t-value comes from. It's integrating, right? This is a Gaussian. It looks something like exp to the minus x squared. I think there's like the square root of sigma is down here somewhere. And you got to actually subtract off the mu right here. But anyway, there's a function that they're integrating. And they're finding the x value where I've covered 95% of the data. Or let's say I wanted 99%. then I would be starting at the left-hand side and integrating until I got, what did I say, 99%? I could go 99% and leave 1% uncertainty. So I can select the level of uncertainty that I'm comfortable with. And typical in engineering is a 95% confidence interval. So that's a one-tail distribution. What's a two-tail distribution? Well, I usually don't know if I'm a little above or a little below the mean. So I want to have uncertainty above and below. What that means mathematically is instead of having 5% here, let's see, I'm going to erase this 1% part. Instead of having 5% here, I'm going to put 2.5% here and 2.5% here. But I'm still going to get that t value by starting at the left infinity and integrating over until I get where I want. In this case, it would be 90. I'm going to have to go over to 97.5% area because that would leave half of the area over here. That's where you get the t values from. The difference between one-tail and two-tail. You almost always want two-tail is the take-home message here. Because we never know if our mean, like our delta p, is a little above the true mean or a little below the true mean. There's some cases where you would want a one-tail, where you want to put all your sensitivity on one side of the distribution. And in engineering, that usually deals with safety factors. Let me give you an example. Let's say I've just developed a drug that reduces cholesterol, better than every drug out there. And so there's value. That's the first thing I want to do, right? I can produce the drug and it's efficacious. The second thing I have to test when I have a drug is that it is safe. And what I usually care about is it is at least as safe as what's currently out there. And that at least as safe is where you would use one tail. I don't care if it's less safe. I want to put all my sensitivity on proving that it is at least as safe as what's currently out there, or that it only has, adverse reactions in a tenth of a percent of the population or something like that. So all I care about is safety. I don't care if it's unsafe. All I care about is safety. That's a case where I would use a one-tail distribution. Things only go one way. Okay, so how do we get the t values? Oh, in fact, let me start sharing my screen one more time over here. There's one little term we have to be aware of. If I want a 95% confidence interval, the alpha value for that is 0.05. My level of uncertainty. That's the alpha value. So for a 95% confidence interval, alpha equals 0.05. You'll often see nomenclature that says 1 minus alpha over 2 confidence interval. And this is to remind you that you have to do a two-tail. I still have 5% uncertainty. Sorry, let's not do cursive here. It's hard to see. My alpha value is still 5%, but to get the right t, because I want some above and some below, I actually had to split this in half and go over to 97.5% in my distribution over here. Does that make sense? You often see the 1 minus alpha over 2 confidence interval. That's a little notation to remind you that I have 5% uncertainty, but to get the right t value, I had to split it in half and go a little further. Okay, let's show you some examples here, because this is often a hard thing to remember what to do. This is documented right here on this little figure. I could have all my uncertainty. Let's go to this one. That's a little better. I could have all my uncertainty on one side. That's one tail, where my alpha is 0.05. For the same alpha 0.05, if I'm doing two tail, then I'm going to put 2.5% on the right and 2.5% on the left. And then this talks about the 1 minus alpha over 2 type notation. So what am I going to do on Excel? I need a t-value. There's several functions in Excel. One is t.inverse. And notice that when I start typing that, there is t.inv and there's t.inv.2t. You probably understand the 2t is the two tail. So let's use two tail. And it wants a probability and a degrees of freedom. The probability is 0.05. It's the alpha value. And the degrees of freedom is n minus 1, which in our case is 4. I'll just copy this out so you can see it. So in this case, the probability equals alpha, and the degrees of freedom is n minus 1. I can actually use the one-tail distribution to get the two-tail value. I just have to know how to manipulate it. In this case, I want to give it 0.975 and 4. If you use the one tail, you want to give it 1 minus alpha over 2. So if you use the one tail, let me move this here. I will say here is two tail, one tail. So here the probability equals 1 minus alpha over 2. Does everyone see where those two numbers come from? I got the same number. One function in Excel says, just give me your alpha value and I'll figure out all the 2t stuff. The other one says, you actually have to tell me how far over on the x-axis you want to integrate, or how much area you want to integrate to, starting at the left and going to the right. Historically, everything has been like this, one tail, but because almost everything's two tail, now they start having these two tail functions. There's one other function you want to see in Excel. It is t inverse, and this is totally confusing. I give it 0.05 and 4. What is this one? This is the same as t.inverse.2t. But you'll notice that when I start typing t inverse, there's this little caution symbol. What's that caution symbol? We saw it when we saw the standard deviations too. So let's talk about what's that caution symbol?
I just mean like it's an old formula in Excel, like it'll eventually go away.
That's right. It's called deprecated. Microsoft, in its infinite wisdom, has said, I don't want to call this function anymore t inverse. I'm going to start calling it t.inverse.2t. And eventually, all your old sheets that you're using t inverse are going to go away. They won't work anymore. It still works right now, but maybe in my next version of Excel, it's not going to work. And so you see the same thing with the standard deviation ones. Notice down here, the STDEV was, you assumed sample, and then you put a P on it to get the population. They decided in the next version to be more explicit and actually make you say either .s or .p. So that's the difference there. So important part about this part of the lecture, you want to know how to get t-values, two-tail, and whatever function you're going to use. Or what if you wanted to use a table? So if you type student t-table, often the one that comes up close is this one from San Jose State. And so let's just kind of go through this. Our degrees of freedom is 4. So we're going to look at the 4 line. And then you see at the top, this is the 1 minus alpha over 2, which in our case would be 0.975. If you look at one tail, the alpha value where you want that you want to integrate to is 0.025. I have 0.025 on the right and 0.025 on the left. Or if you say, if I'm assuming two tail, then I have a total of 5%. That's how you read this. And then you go down to 4 and you get the 2.776 that we've seen. You've got to be familiar with understanding what all of these tables mean. What's it mean when it says one tail, two tail, what functions to use. And in fact, let me bring up Python, because often you guys are using Python. And the library, let me import. The library is import scipy.stat as, what do I want to do it? Or actually I do from import, I think it's just called T. No, maybe it's stats. There we go. So let's create a quick array. Let's say what, x is equal to 1, 2, 3. The t value function is going to be t.ppl. I think that's what it is. And then I'll look at my notes here in a second. Let me get my notes real quick. I don't use Python a lot to do stats, so I always forget what it is. I'd have to look it up online, or it's PPF. So there's our 2.776. So in this case, you want to use the 1 minus alpha divided by 2 notation for your probability. So this is assuming one tail. You got to know you're going to split your 0.5 into 2.5 on one side, 2.5 on the other, and then so I'm going to have to integrate over to 0.975. Okay. You're going to want to be familiar with how to use Python, with how to use tables. Whoops, sorry. With how to use tables right here, or how to use Excel, or whatever you care about with your whatever program you're using. Okay, so the final thing is, how do I get a confidence interval? The equation for the confidence interval is the standard error. So that is S divided by square root of n, which is 5, times t. I'll just put S divided by square root of n times t. And so what I would say here is my...
You said the standard error, or did you mean the standard deviation?
No, actually, this is the standard. Remember, this is the standard error. S divided by square root of n. That's what this is. So this part of it is the same. S divided by square root of n. Does that make sense? And then so the only difference between standard error and confidence interval is this one's multiplied by t. Does that make sense? So this is S divided by square root of n. Does that answer your question?
Yeah, it does. Thank you.
So you'd say something like that. The error, or my average, or my pressure drop at 7.2 gallons per minute is 43.38 plus or minus 0.13 at the 95% confidence limit, or confidence interval, where the uncertainty is the confidence interval, something like that. Okay. What if I wanted a 99% confidence interval? What would I do? What's the only thing that would change?
Alpha would change.
Okay, yes, alpha. In fact, let's put an alpha here. Right, alpha would change. So it would be 0.01 now if I was at 99. It would be 0.05 for 95%. And then here, instead of putting 0.05, I would put 0.01. And do you expect to have a bigger number or a smaller number than 2.77? So if I move from 95 to 99, should that t-value get bigger or smaller? Any ideas?
It'll get bigger, won't it?
It will get bigger, right? So now, and this gets bigger, so my error gets bigger, right? So at 99, it's 43.38 plus or minus 0.23 at the 99% confidence interval. That makes sense, I think, if you think about it, because if I want to be more sure, that means my error bars have to be bigger. And so if I wanted to reduce the error at the 99, I'd have to keep taking more n. And that would allow me to reduce my error. And standard in engineering is 95. Maybe if you're doing something with NASA and you want this Mars rover to last a long time in space, maybe you're doing 99% or something like that, but standard is usually 95%. What does that 95% confidence interval actually mean? Well, if you talk to a statistician, what they'll tell you is that what a confidence interval means is that if I did this exact same experiment where I took 5 data points and I came back tomorrow and did the same thing, and then I came back tomorrow and did the same thing, it means that if I did it for 100 days, 95 of those days, the true mean would be somewhere between inside my range of data. Now that's a little weird. So in engineers, we just say we're 95% confident that the true mean is between plus or minus 0.13 of 43.38. Okay, that is all we need to talk about for basic stats. You want to be able to understand what is, how to calculate confidence intervals, the difference between standard deviations and confidence intervals. In fact, I want to do one other thing. So never use S as an error. So when is S ever useful then? It's used all the time in engineering for process control, because S should not change as long as my system doesn't change. I can use that to make sure that my system is staying in spec. So I've got these plants or these processes that have been running forever, and I'm measuring temperatures or pressures or concentrations. And I know, because I've taken them for so long, what it should be at. So let's say in hour 1, I take a reading and it's right here. The next hour, I might be right here. How do I know if those are good values? Well, I also know that what the standard deviation is of this process. So plus or minus 1 sigma would give me about 68% of the data. Plus or minus 2 sigma, I should be 95.4% of the data. And plus or minus 3 sigma, I should be 99 point something. So if I'm randomly taking samples, I took, say, 1,000 of them, I expect 990 something of them to be within plus or minus 3 sigma. So what happens then if I'm going along and then in hour 3, I'm out here? What am I going to do?
Be very suspicious of that.
Yes, I'm going to be very suspicious, because 99.7% of the time I should not be out there. But this could be the 0.3% of the time that natural variation should be out there. So usually what I'll write in my policies and procedures is, okay, let's take another point at, say, 15 minutes and see if it's dropped back into our expected range. So after 15 minutes, if I take another point and it's down here, I'm probably okay. But after 15 minutes, if I take another point and it's up here, then the likelihood that I have 2.3% random events happen like that is fleetingly small. And I'm going to say, okay, I got